Hello, everybody. Thank you for coming for this MEG workshop. My name is Dimitrios Pantazis. I am a principal research scientist at MIT, and I also direct the MEG facility. And together with Ev Fedorenko, we decided to organize this workshop for two reasons, mostly. One is that there are several new users interested in using the MEG facility, which is very exciting, and of course it would be useful to get to provide some background on methods and data analysis. And another reason is that MEG has a decades-long history of developing methods, and during this time, methods became, to some extent, more complex. There are several methods for the same function, and it can often be confusing and challenging, but of course, there are also great opportunities as well, given that algorithms have tuned to different cases and different experimental paradigms. So today we'll have three talks. Focused in different aspects in methodology. The first one will be about localization methods and the great variety of methods that exist and how they can provide solutions in different circumstances. The follow-up talk will be about decoding and how it can be used to extract information from brain signals, from MEG signals. And the last one will present connectivity measures and how we can construct brain networks and infer how different brain areas communicate one another. And the workshop will conclude with some demonstration of the Brainstorm software that we use to analyze data. That's not the only software available. As I will describe, there are many valuable packages to analyze data. The presentation will be focused for users that want to collect data in our facility and analyze the data, but it will also be useful for other interested researchers to learn, to get a general idea about what MEG data analysis involves. So without further delays, let me introduce the first speaker, Matti Hämäläinen, who is a professor of radiology at Harvard Medical School and director of the magnetoencephalography core at the Department of Radiology, MGH. He's one of the pioneers in the application of MEG in conjunction with other non-invasive functional and anatomical imaging methods to study human brain function. He has had a crucial role in developing whole-head MEG instrumentation, analytical methods and tools, as well as experimental protocols, which have together paved the way for MEG becoming an important basic research and clinical tool worldwide. And let me also emphasize that, in my opinion, it's hard to find other researchers that has as much or more impact in MEG than Matti, because of his valuable contributions over all these years. And if I were to select three contributions that, to me, really made a difference, he was the key person to introduce minimum norm estimates in the MEG field, and we use minimum norm estimates all the time to reconstruct brain activity on the cortex. So it was a very valuable contribution. In the 80s and 90s, he contributed software that became the foundation of Neuromag, the main MEG company, or one of the main companies over all these years, and his software was in the heart of our analysis. And also, Matti was the developer and the principal investigator of the MNE software, which I will not be describing today, apologies for this, but it's among the most robust ones and the only one with a Python implementation, so that's really unique. And most important of all, Matti was also instrumental in helping me end up in my position here at MIT, and forever I will be grateful. So thank you, Matti, and please come over.
Thank you, Dimitrios, for this kind introduction. So Today I have entitled my talk a little bit maybe in an advertisement way, saying that the source estimation approaches constitute a spectrum of purpose-built optimal tools, and you will see during this talk what that means. In the corner you see me using an optimal tool for nails, probably on a spring Sunday because I am wearing a collared shirt. So the whole point of source estimation in MEG is that we want to, instead of dealing with the measurements on the MEG helmet, we want to know what the brain activity inside is. And that is, we want to make an estimate of the not only the signals but the sources in the brain. And this talk is all about what kind of information we use to do this, how exactly is this done, and especially I have several examples of discoveries made with different source estimation methods, which I hope illustrate to you that in different cases you need different tools. There are nails and screws, and there are, like in computers now, many kinds of screws with different kinds of bits needed to open and tighten them. So my overall content is to first talk quite in length about the relationships of sources in the brain and the fields that we measure in MEG and EEG. Then I will discuss in particular the use of dipole models and what kind of discoveries have been made with it. And then I will talk about distributed source estimates and come up with some conclusions. But first about the sources and fields. So the sources are inside the brain and the fields are measured either on the MEG helmet or with EEG electrodes on the scalp. And in this sense, MEG and EEG are very much related. The only difference is that EEG measures the electric potential on the scalp and MEG measures the magnetic field outside the head. But in both cases, the original sources of these signals are the same. They are the neural currents. Sometimes you hear that EEG is produced by volume currents, but physically speaking that is wrong. The volume currents are actually the EEG. They are like EEG, and volume currents are like two sides of a coin which cannot be separated from each other. So both are generated by the same sources. They both have a reasonable spatial resolution. If you think about the optical spatial resolution of being able to distinguish two sources, the rule of thumb literally applies, so that the sources need to be a couple of centimeters away to be distinguishable from each other. And especially MEG and EEG are real-time measures of the actual brain activity. That is, they record millisecond by millisecond what the current distribution in the brain is. And from this it follows that you can, for example, derive frequency-specific measures of association, that is connectivity, so that we can calculate connectivity in different frequency bands. And in fact, recently we published a paper where we studied the evolution of certain network characteristics in the brain as a function of not very short time, but years over the age. And we found that the beta band, the 20 Hz band activity behaves differently from the higher frequency activity. And if you think about fMRI, these two things are lumped together, so that MEG and EEG potentially give a more colorful picture of the brain activity. And in particular, the maturation in the beta band was linear, whereas in the gamma band it basically saturates over time. Another consequence of being able to measure this millisecond by millisecond brain activity is that we can relate, with help of biophysical models, the MEG and EEG measurements to models of the neural circuits. So we can use a model of a neural circuit and make a proposition what might be the microscopic cause of the time courses of the currents in the brain that we observe. Another consequence of this kind of a model is that the data can be compared across species, so that the same model can be in certain cases used to predict the animal invasive electrophysiology. And this is the work I have been involved with, working with Stephanie Jones and Chris Moore at Brown University. And we have actually recently published a paper in which we looked at the same phenomenon in not only humans but also in monkeys and mice, and were able to show that there's the same basic neural level mechanism that can explain the signals in all three species. Now, what are the actual causes of MEG? So this audience of course knows very well about the action potentials and the postsynaptic potentials that follow in the cells. And the time courses of these are such that the action potential time course is very fast, whereas the postsynaptic potential time course is slower. Another important difference is that the currents related to the action potential correspond to an opposing current pair which has current flowing forwards and backwards. And that's why it's difficult to see anything from the action potentials far away, because these signals from these two currents cancel each other. So that we believe, on the basis of this current configuration and the time course, that the MEG and EEG signals on or outside the head mostly are due to postsynaptic currents. And the amplitudes of these signals are such that the EEG amplitude is between 1/10 to 100 microvolts, and the MEG amplitudes between 1 femtotesla, 10 to minus 15 Tesla to 3 picoteslas. So it's difficult to of course to say how small these are, but one figure of merit would be that in modern MEG instruments the white noise level is about 2 femtoteslas in a unit bandwidth, meaning that if we measure at 10 Hz bandwidth, the noise is about 3 times higher. So that these signals are in fact quite reasonable to measure. And regarding of how many cells in the cortex might be responsible by the signals we observe, we made an estimate early on that it might about 500,000 synapses might be required to produce a current of 10 nanoamp meters, which we measure typically in MEG of that order. Later on, Murakami and Okada used a much more sophisticated model, and they fortunately came into the conclusion that the number of cells is probably about 10 times smaller, so that tens of thousands of cells are probably going to be synchronously active if we observe these kinds of signals. Another important basic level information is that it has been shown with measurements and also with models that the amount of current, the current dipole density per surface area is pretty much constant across species and also across brain structures. Meaning that you can make a rough estimate of how big an area of a cortex is active once you have a current amplitude of, let's say, 20 nanoamp meters. That would mean about 20 square millimeters or larger. So maybe the range is like from 0.1 to 1 nanoamp meters per millimeter squared. So this is very important to realize that in this sense MEG and also EEG give quantitative estimates of the actual currents in the brain. We are not looking at any kind of statistical test variable, but we are looking at the physical quantity, and you can actually probe that physical quantity also with direct measurements from the brain. So in that sense, there's something really to grasp in when you look at MEG signals, and especially at their sources. And therefore you can also get the sense whether something is signal or noise from these amplitudes, because there are some typical amplitudes which you should observe. Now, to understand how these signals then are converted to the measured fields, we need what is called a forward model. That is a solution of Maxwell's equations in the case of the head. And if you look around, it's very clear that the sphere model is a good approximation. Here is a typical subject, and then you fit the sphere to his head, and it's perfect fit. You notice that there are these different layers on the sphere, and they correspond to layers of different conductivity in the head. That is the scalp, the skull, also the CSF, and then the brain. And now it happens to be so that if you replace this multi-layered structure with a single layer, a homogeneous sphere, it turns out that MEG remains unchanged between these two situations, where EG is clearly different. And this means that you can accurately compute MEG with less information about the actual conductivities in the head. So really the conductivity doesn't matter, and you don't need to take care of these layers. Even when you go to a next level approximation, a boundary element model, the situation is such that MEG has some practical benefit, and that is caused by the fact that the skull, which is between the brain and the scalp, has a very poor conductivity. It's almost an insulator. And we came up in the 80s with the proposition that maybe you can get quite an accurate result actually by replacing the skull by a perfect insulator. And in fact it turns out to be so. And as I mentioned, this was proposed in 1989, and then actually Yoshio Okada and co-workers in 1990s made an experiment where they measured MEG and EEG signals from a swine. So they actually made an opening in the skull and removed the flap of skull and saw whether the MEG signals changed, and they didn't change much. And then they put the flap back and were able to repeat this experiment. So with this in mind, let's see what follows from the fact that the head is almost spherical. And what follows from it is that radial currents don't contribute to the magnetic field B outside the head. That is, for any current that is flowing to the direction normal to the skull, we don't get any magnetic field outside. On the other hand, if you look at the cortex, there are these large pyramidal neurons densely packed, and they have dendrites which have a very preferred specific direction normal to the cortex. And this geometry guides the currents so that they are normal to the cortex. And on the other hand, from that it follows that if you look at the fissure, the currents normal to the cortex are tangential to the scalp, and therefore both MEG and EEG are non-zero. Whereas at the crests of the gyri and the troughs of the sulci, the currents are radial, and you don't see any MEG signal from these locations. And in fact, in the MNE minimum norm estimate paper that Dimitrios mentioned, we made the prediction that it would be desirable to improve the minimum norm estimates by finding ways to inject some a priori knowledge or assumptions of the experimenter. For example, one could confine the integration area to be the cortex. And this actually was practically made possible by the work of Anders Dahle and Matti Sereno, and then later Bruce Fischel, because now we are automatically able to construct the geometrical description of the cortex and use that as the basis of the source estimation. And as you know, the cortex can be inflated so that we can actually look at the fissures, which is important for MEG because the signals come from the fissures. So to repeat, for MEG, if the source is tangential, that is, current is flowing in this direction, and we have around the thumb direction of the current outgoing and ingoing magnetic field, we get the MEG for the tangential part. For the radial part, which is pointing towards you, we don't get any MEG, and if the source is tilted here somewhere halfway, we get like a fraction of the first pattern. Whereas for EEG, we get an orthogonal pattern for the tangential source, which is pointed in this direction. We get the peak for the radial source, and when the source is tilted, we have a combination of the two. So that MEG is composed only of one prototypical field pattern, whereas EEG has two. And this complicates the analysis of EEG on the basis of just looking at the signals. On the other hand, if we look at the cortex and plot the total signal amplitude at different locations, the situation is the following. I will come here so that I can point better to the correct location. So here is the Rolandic fissure, and this is the motor cortex, and this is the somatosensory cortex. And if we in MEG go down from the crest of the gyrus, there the source is radial, so that we don't see any MEG, then the MEG signals grows very quickly when you go down, just turn a little bit tangential, and then finally is totally zero at the trough of the sulcus. EEG, on the other hand, is strongest here at the crest of the gyrus and goes continuously down when the source moves down. This means that EEG is dominated by these radial currents, and that explains why in many cases MEG has been very useful in understanding what is going on, because there are situations where we are interested in what is happening in the sulci and not so much in the background activity in the gyra, which has a strong component in EEG. For example, it was long believed that the auditory late evoked responses are actually generated by something happening in the frontal lobe, which is consistent with the radial source pointing into the brain in the front, because you see a big negative EEG component in the frontal parts of the head. But MEG clearly pointed to the direction that the sources are on the two auditory cortices, because you saw these two separate field patterns, and you could see clearly the activity from the two auditory cortices without further ado from the MEG measurements. And it's curious that there was a paper in the 70s suggesting that this might be the case also for the EEG, but since the frontal lobe explanation was so much fancier, nobody believed this paper, which was very technically competent. So don't always believe what other people say. So then it's important also to understand what we measure. In the MEG system you have here the triax and the vector view. We have at MGH we have these triple sensor units, and there's a reason for having these triple sensor units, which contain a magnetometer and a planar gradiometer. And that is that the magnetometer measures this magnetic field profile with the plus and minus above focal source. But if you take a derivative of this measuring the planar gradient, then you get a peak above the source, and therefore it's as a first approximation easy to look at the planar gradiometer patterns and see approximately where the sources are. And for example, you could very directly see that the background activity, the spontaneous rhythms, are modulated specifically at specific regions by by different conditions. There are eyes closed, eyes open, move left, move right conditions. And you can see that in the eyes closed condition, the 10 Hz component alpha is much stronger in the occipital sensors than when eyes are open. And similarly, this two-peak structure near the motor cortex is clearly dampened by movement. That is by finger movements in this case. So that these background activities are differently modulated by external events, and you can sometimes see it directly in the data. Now this has been kind of halfway through the talk and useful background, I would say. And now let's go to the MEC and EEG source estimation. Almost everybody knows about the inverse problem, in the sense that there's an inverse problem in MEG and EEG. And what that means is that in the brain we have currents, and then we measure MEG and EEG, and this relationship between the currents X and the measurements Y is governed by the forward solution, by the Maxwell's equations. There's nothing particularly exciting about this relationship. It just requires skill and care to calculate this gain correctly. In addition, there's of course noise. But the problem is that once we have the measurements Y, the noise, and the gain matrix, we want to calculate the inverse estimate. We want to calculate what might be the current underlying this measurement. And unfortunately, this problem is ill-posed, which means that there are potentially many current distributions which explain the same data, and even more importantly, the solutions may be sensitive to noise. So we need to do something about this. But to illustrate this further, the situation is like in this my favorite cartoon, where this dinosaur has died a long time ago, and then the paleontologists come up to dig up the bones, and then they make a source reconstruction of the dinosaur, which is almost successful. Now, unfortunately, many people take this being not at all successful, but in fact it is in many ways successful. You can see that the dinosaur stands on 2 feet and has a tail, but some parts are just misplaced. And once you know which parts are likely to be misplaced by the MEG-EEG source reconstruction, you can usefully use the source reconstructions for your benefit. The reason why there are many possible solutions is that there are silent sources. We saw already one, which is radial current in a sphere that doesn't produce any MEG. On the other hand, if there are current loops in the brain, which is unlikely, then there will be no EEG. And the third possibility may actually occur if there's a closed surface and uniform current across the surface or throughout the surface, then there won't be any MEG nor EEG. So this is a little bit depressing, but let me make it a positive twist and say that we have many ways to make the problem unique. So, and these many ways are characterized by how they behave in different situations and what kind of assumptions we put in. So, parametric models and current distribution models are what I am going to talk about. In parametric models, we assume typically that there is a limited number of dipoles. And therefore, the problem of finding their locations and orientations and amplitudes is overdetermined. So there are more measurements than source parameters, and we obtain solution by least squares fit. In current distribution models, on the other hand, we have many sources on the volume or on the surface, and therefore we need an additional constraint which selects what kind of an estimate we prefer. And in the minimum norm estimate, we make the condition that the overall power of the current would be minimized. But then in sparse estimate, we typically use the L1 norm, which is sum of the absolute values of the current. It's important to realize that neither the L2 MNE nor the L1 so-called minimum current estimate are based on a physiological fact. Maybe the L1 norm estimate more, but certainly L2 norm estimate is characterized by its ease of computation, and maybe L1 norm estimate by the fact that the dipole models have been so successful. So there isn't really a good justification for using either of these models, but they still are useful in practice. Before moving to the actual estimates, let me repeat some terms. We have seen that it's reasonable to have the elementary source in the brain be a current dipole, a source and sink of the current because of the organization of the neurons. On the other hand, the inverse model could be defined as the definition of what kind of an optimal solution we want. And then we often hear about focal sources, which means activated areas of small extent, or extended sources, activated areas of larger extent, and it should be said already now that it's difficult to differentiate between these two. Then distributed sources I would reserve to the concept of having multiple extended or focal sources in different areas of the brain. And then finally the forward model is the recipe for solving the Maxwell's equation in the case of the head. So, about the parametric models, I have entitled this section Discoveries with Dipole Models. And the idea in the dipole models is really that we are so far from the actual sources that the neural currents on a few square centimeter patch of cortex look like a dipole from a distance. This look like is important to understand. This means that we equivalently replace this patch of activation with the dipole. We don't think that there are dipoles in the brain, but we think that this is a useful description of the activity of a patch. And typically we fix the dipole locations over time and then let the amplitudes vary over time, and this type of a model was promoted early on by Michael Scherk, first for EEG and then for MEG also. And in fact, the idea of a dipole was pointed out very early on in the MEG field because like it's mentioned in this early somatosensory evoked field paper from Sam Williamson's group, it looks like really on the scalp we have a field pattern which could be accounted for by a dipole. And talking about this focal versus extended, this is just a toy example. I in simulation activated an area like this in the auditory cortex and then found the best fitting dipole, and in fact this best fitting dipole explains 99.9% of the variance in the absence of noise. So you cannot differentiate this kind of an activity of a patch which you see in red in the MRIs from the dipole which you see in green. So the fact that the dipole is not quite where the patch is of course that it's on the parietal lobe side in this inflated view of the brain, and therefore it's very close actually to the red patch in the cortex. Now, the challenge in this type of dipole estimates is the fitting, finding the best solution in least square sense. That is, we compare the measured and data to that of the model, calculate the L2 norm, and then move the dipoles QP and their locations RP so that we obtain the best fit. And this is in principle done so that you select a number of dipoles, select initial guesses, then you can use a linear fit for the amplitude, so you fix the locations and orientations of the dipole, determine what is the smallest least square error, and then if that error was the same as in the previous step, you stop, and then you find better candidates for the dipole locations. Unfortunately, there are these steps. One, select a number of dipoles, select the initial guesses, and find better locations, which are not trivial things to do with multiple dipoles in the works, because it turns out to be a nonlinear inverse problem. So therefore, people have developed some partly heuristic strategies to use the multi-dipole model. This is not as bad as it sounds, because with this kind of an approach, you at the same time model and understand your data. The modeling process is not separate from the understanding, whereas when you do distributed source estimates or typically analyze fMRI data, you do the analysis and then you try to understand what the analysis means. This heuristic just means that in the dipole analysis you typically model and try to understand at the same time. And typical strategies that have been used is to try to select time points where only one dipole is active. And this works often very well with sensory responses, because early on only the primary area is active and then you can add more sources to that. Or use only part of the data to get initial guesses for the dipoles, because the dipole field patterns are confined in space. That is, you construct the model dipole by dipole. And what that means is the following. Let's look at this case of somatosensory evoked responses. So early on, at about 20 milliseconds time point, there's only activity in the primary somatosensory cortex. And it's almost a perfect focal source in the somatosensory cortex. And you can fit the dipole at that time point. But if you look at the data carefully, then you already at 35 milliseconds, 15 milliseconds later, see that the data are different when you look at them at the sensors. And in fact, if you at 35 milliseconds fit another source, which is this darker yellow curve here, then you retain the 20 millisecond source and get the new source at 35 milliseconds. But if you look at the goodness of fit, there at later latencies you don't explain the data at all. And that is because the S2 areas will be active, and when they are added to the model, you get a nice about 90% explanation of the data all the way through, except for times where the signal goes down. Now it's important to notice that this N20 and P35 components point into different directions. You see these two orange arrows in the primary somatosensory cortex here. And this means actually that it's likely so that the N20 component reflects input from the thalamus to the deeper layers of the cortex, and that causes the current to flow forward, and then there is already cortical connections at the later time with input to the superficial layers, and that causes the current to go inwards. So in this sense, the current directions are important. Now, when we had the first whole head instrument, we by accident almost found that in addition to this primary somatosensory cortex source, there's a later activity very close but more posterior to the primary somatosensory cortex. And we found actually that this activity came systematically from so-called posterior parietal cortex, and it was systematically posterior to the primary somatosensory cortex, and that can be shown shown here also on the then from now today's point of view primitive MRI surface reconstructions. And actually we very early realized this, that if you measure MEC all over the head, you really get qualitatively new information from the human brain. And this is, I think, a challenge to any of these new sensor technologies that are coming online. Do they provide qualitatively new information? Is it so that whatever you measure, you get something new? And that remains to be seen. But anyway, we measured, for example, the activity in a picture naming task, so that we could see the activity in different areas of the brain. Then it also happened that when we tried to see what the eye blinks look like in the whole head MEC instrument, we saw activity in the back of the head, which was systematically related to the eye blink and was systematically located in the posterior parietal occipital lobe juncture. And it turned out that actually a viable explanation for this is that this area somehow maintains our visual reality, so that our missing observation is corrected for afterwards. It's interesting that this was half an accident, but then led to a Nature paper when we were able to connect the dots. So it's important to be open-minded when you look at your data. If we would have looked only at the frontal sensors, we would have never observed this. So another case was that we similarly wanted to see what saccades look like, and it turned out that related to the saccades we have activity very low in the sensor array, which corresponds to activity in the cerebellum. And the cerebellar activity, which is related probably to the movements, remained the same independent of whether lights were on or off in the room, whereas the posterior parietal cortex activity, which again had this maintenance role, disappeared when it was dark in the room. And then we saw that in several subjects the signal time courses were similar and the source locations were reasonably similar also. And we did all kinds of experiments. For example, we let subjects imitate orofacial gestures and were able to follow the activity from the occipital lobe to STS, inferior parietal lobe to the frontal lobe, and finally to the motor cortex. Interestingly, in subjects with Asperger's syndrome, there was a delay in this frontal cortex activity, probably related in the difficulty to relate other people's actions. And we also looked at locations of spontaneous activity with dipole models and found that related to movements, the 10 and 20 Hz activities behave differently in time. And interestingly, only the 20 Hz component of the so-called mu rhythm in the somatomotor cortex follows the homunculus. The 10 Hz component does not. And this is probably related to the importance of hands in our life. So I hope I have, with this quick potpourri of things, shown you that by correctly using the dipole models, many interesting things can be found from the brain. So dipole models can be used in a wide variety of situations. And in fact, the multi-dipole model can be considered to be an interactive hypothesis testing tool. So you could build the model, check the model significance, that is to ask the question, should we reject this model, check the parameter significance, that is compute the confidence intervals also. But for all of this to succeed, we need a reasonable estimate for the noise. And it's important to notice that in the dipole models, cortical constraints are usually not applied, and this is because if you don't apply the constraint, the dipole positions and orientations can compensate for an inaccurate forward model, and it turns out that then the time courses of the sources are more accurate and don't mix with each other. And then you just need to interpret the dipole locations correctly, and it often turns out that they are a little bit on the white matter side, but that just means that either the forward model is not accurate exactly, or that the source activity is actually not very focal. And again, the dipoles are equivalent sources. The information about the extent of the source is only indirect in the amplitude of the source through the Okada constant. So one characteristic of these dipole examples is somehow that the statistics is not really necessary. I only conduct experiments in which the result is clear, which is a quotation from my countryman Ragnar Granit, supposedly. So in all of these experiments we were able to essentially look at individual data. Now, as a result of a long sequence of development, these anatomically and functionally constrained source estimates came into use. And we already saw something related, which is the ability to reconstruct the cortical surface automatically from the MRIs. And in particular, in the minimum norm solutions, we have the grid of dipoles usually on the surface. We have many more sources than measurements, and therefore we need to meet another optimality criteria besides the one which compares the measurements y to the predicted measurements g times the dipole amplitudes. And this criterion is added to the cost function, and the simplest one is the minimum norm estimate. But there are other possibilities also. Of course, we talked about the discrete dipole model before, but in addition to the minimum norm estimate, we can obtain a sparse estimate by minimizing, instead of the sum of the powers of the currents, the sum of the amplitudes of the currents. And we can do more complicated things with the so-called mixed norm estimates, which can be sparse in space but smooth in time. So this illustrates the situation. So the minimum norm solution is smooth both in time and space. So every point in space has and time has a non-zero value. When we use the minimum current estimate, the L1 estimate, at different times, different discrete locations in the space are active. But we don't really like this very much, because the activity tends to move around in the vicinity in a jerky way, and then unfortunately these minimum current estimates have been used so that you actually smooth the sparse estimate across the neighboring locations. Then with 1 May O we introduced these so-called L21 or L12 estimates, in which the solution is sparse in space and continuous in time, in the sense that if the source is active at a certain location in time, it's always more or less active. And finally there's a variation of this called time frequency minimum mixed norm estimate, in which we allow the sources come on and off so that they are periodically on and off in time. So early on, when we used the minimum norm estimate, nobody believed, even though in this visual experiment where different octants of the visual field are stimulated, you can see symmetry between the left and right, and also between the between the lower and upper visual fields, but this is not yet very convincing. I think people became convinced when the MNE was so to speak, modernized. So first of all, the source locations and orientations are constrained to the cortical mantle. The forward solution is calculated with the boundary element model. We use better noise estimates, and we display the data on an inflated cortex to reveal the sulci. And finally, we compute statistics, convert the data to a statistical test variable, and are able to compute combined MEG and EEG solutions, and also fMRI guided solutions. And we already saw this benefit of constraining the orientation of the sources. And if we compare the minimum norm solution and the so-called DSPM, which is a statistic, without orientation constraint, the MNE tends to be very superficial, because MNE likes small currents, and smallest currents to explain the data are obtained when the sources are close to the sensors. Whereas when we constrain the currents to be normal to the cortex, we get a more reasonable solution in this auditory measurement close to the auditory cortex. And we can also combine MEG and EEG with these estimates, and what is plotted here is the point spread function of these estimates for MEG and EEG, and MEG and EEG together on the cortical surface. And then you can see that in this combined case you see more of the cortex, that is the point spreads are smaller. So there's really benefit of combining these two measures, and it turns out that the combination is super additive, so that you cannot obtain the same result just by adding more MEG channels. And a few examples of how these methods could be used in a more interesting way. In this scene, the different parts of this ambiguous flicker at different frequencies. And if you look at the MEG signals in the back of the head, you see 15 and 12 Hz peaks in the spectrum corresponding to these flicker frequencies. And when the subject reports a change in the percept from the waist to the faces, you can see a change in the dominant frequency in the data, so that we can kind of eavesdrop what the brain is doing. And we can get a more quantitative measure of this eavesdropping signal by looking at the signals in the brain in the source space and making a linear regression with respect to the tag frequencies and other nuisance frequencies, so that we get the amplitudes of these tag frequencies. And it turns out that the significant signals in either of these tag frequencies are in the occipital cortex, and there's in this circled area there's a significant difference between the two percepts. So by cleverly using these source signals, we can get more information in the brain space. Another example is measurement of connectivity after showing typically developing an autism spectrum disorder subjects pictures of faces and houses, and then it turns out that the difference between faces and houses is that if you calculate connectivity from the fusiform face area to other parts of the brain, there's a difference specifically to these three different regions at different times. And it turns out that this difference is actually slightly even reversed in the ASD group. So that really there's something abnormal going on in the connectivity. And this is long distance connectivity, but since MEG has a good temporal resolution, we can also look at local connectivity in the fusiform face area, which we defined on the basis of evoked responses in the sense that we can look at phase amplitude coupling. And there is really very clear phase amplitude coupling between low frequencies and higher frequencies in the FFA, and specifically in the FFA, and there's a difference between houses and phases, but this difference is missing in the AST group. So one can really get meaningful information in the brain space by looking at the source signals instead of the sensor signals. Then finally, about fMRI guided estimates, this method was introduced at the turn of the century by Anders Dahle and co-workers, and the idea is that you make the sources more likely to occur in locations where there is significant fMRI activity. And in the original Neuron paper, they showed that by doing this, the focality of the MEG source estimates improves, and this has been to some extent used in experiments, even though it must be said that doing this combined experiment is extremely tedious. Let me, for the benefit of time, jump a little bit forward. And this is an interesting note that sometimes it's actually more interesting to look at fMRI and MEG in relationship to each other. And this is the work with Dara Manoa, in which we tried to find where the so-called error-related negativity happens in the basis of MEG and EEG. ERN is a kind of an oops signal related to committing an error in a task, in this case, the Saccard task, where you were asked to move your eyes either in the direction of a indicator light or in the opposite direction. And from fMRI, the conventional wisdom was that the anterior cingulate is active in the case of errors. And surprisingly, from our MEG and EEG data, looked at it's the posterior cingulate, as you can see here. So this is fMRI, and this is MEG and EEG. So the MEG and EEG data in this sense different from the fMRI data. And in fact, it turned out that other EEG measurements at least had found the same. They had just reported that it was still anterior cingulate, even though it was clearly posterior. Fortunately for us, it turned out that there was a subsequent monkey study which confirmed this finding that clearly the electrophysiological data comes from a different location than the fMRI data. And this is reflecting the fact that these two methods see different aspects of brain activity. So I have briefly covered what I call MNE and friends. And these are distributed solutions which use cortical constraints. And if one uses MNE, the source extents are not true. They are overestimated instead of being underestimated, typically like in dipole models. The sparse estimates, on the other hand, resemble the dipole solutions, and normally non-parametric statistics are used in group analysis. And I must say that pooling these sparse estimates is still a challenge because they may not overlap across subjects. And I would say that comparison with fMRI is often more useful than fusion with it. And I would like to remind you of the ambiguity in the sense that if you have in the brain a focal source, you measure this field pattern in MEG, you calculate the current dipole solution, an equivalent current dipole is exactly the source. But you can also calculate the minimum norm estimate, which is more widespread. On the other hand, since the minimum norm estimate produces the same field pattern as the dipole, you can imagine that there was this distributed solution in the brain. And then you get exactly the same field pattern as with the current dipole, and when you fit the current dipole, you get the current dipole back as expected, but you get also the minimum norm estimate back. So the conclusion is that both MNE and the dipoles point to the approximate location of the activity, but the extent of the activity is difficult to determine. So there's this kind of ambiguity. And as Dimitrios already pointed to, there are many open source or academic software packages which have a very important role in practical MEG analysis, including MNE and Brainstorm, and also other software packages. And in particular for MNE Python, Alex Cranford has had a big role in producing this package, which doesn't follow the meaning of the word academic of no practical importance. So, so finally, general comments. So I would say that different source estimation methods give converging evidence when interpreted correctly. So the understanding what is happening is really very important, so that, for example, dipoles are equivalent sources. They don't mean that the source is really point like in the brain. And especially the dipole examples, I think, illustrated that exploration and hypothesis-driven approaches should be used in conjunction. And it's more evident, I think, in MEG and EEG than in fMRI, for example, that scientific questions, experimental design, data analysis approaches, and interpretation are interconnected and interact, so that you should take somehow in account what can be done later, and not be stubbornly fixated on your particular solid question, but you should be willing to adjust your question so that it can be answered. And really, initial lack of formal hypotheses, like in the eye movement and blink cases, doesn't imply that your data analysis methods are not principled and you cannot get principled results. And in particular, conventional wisdom may be wrong, and it turns out that it's not really useful to use the hammer to drive in screws, but use the best tools for the particular purpose, so that you get the most useful answers. So I would just like to mention all my colleagues and friends from this community, and thank you for your attention.